Hi and welcome back everyone to the second day of the lecture on the smart grid architecture model. And today we are going to looking on how to apply this concept in practical development. So before we start, just take a brief look at what we have so far. So we already have some understanding on the motivation and some understanding of the basic concepts of the smart grid architecture model. And we already know how the SGAM-based viewpoints and model kinds can be aligned with the generic modeling stack that we have discussed in the last lecture. What is missing so far and what we're going to look today is the following topics, like how can we apply these concepts to practical architecture modeling, what could serve as a reference architecture, and do we already have some ideas on solution development? So in that case, I would like to share some insights on some practical applications with you. So following this, the agenda for today will cover a basic introduction to the fundamental topics systems engineering and model-based systems engineering. This is something that we need when it comes to modeling. Then we make a mini excursus on the development of domain-specific languages before we jump over and take a look at reference modeling concepts and some insights to real-world application examples. Okay, so let's start. In the following chapter, I want to spend a few minutes on a discussion on the topic of what is systems engineering and what is model-based systems engineering. These two topics could easily fill individual lectures, but I integrate these elements here because I think it's important to understand the theoretic foundation of all the modeling concepts that you're going to apply. So first of all, what is the big deal with systems engineering? And the main aspect here is that people identified that during the development of huge systems or complex systems, most concepts already achieve a level of around 70%, like here, in a very early design and concept phase. This means that the huge number of aspects are already defined very early in the project, when probably you do not yet know anything, and changing things later will be very cost intensive. So the idea from systems engineering originally was that you spend effort in the early phases when it comes to requirements engineering, concept development, and architecture development, just to save some cost. The other aspect is that by putting effort in something that we call front loading, like spending time and investment at the beginning of a project, you get some more solid and robust designs, which typically will help to reduce the risk. So there are different considerations behind these few words that you probably may research for yourself. I just would like to introduce the basic definition of systems engineering, which is explicitly focusing on being an interdisciplinary approach and means to enable the realization of successful systems. And it focuses on holistically and concurrently understanding the stakeholder needs and exploring opportunities, like understand the goals before you find the solution, documenting, or better said, specifying, deriving and specifying requirements, synthesizing, verifying, validating, and evolving solutions. And to always apply a mindset like think bigger, which means to consider the complete problem before focusing on small solutions. So simply said, systems engineering is a scientific discipline that aims on the question, How can we integrate the different disciplines? How can we start thinking from a system on a system perspective? And what's inside the box is already an individual field of work, which also is guided by different ISO standards. Like, for example, one very famous one is the ISO 15288, which is basically a process framework. And this process framework that we have, it tries to give us guidance on what needs to be done during development. And this is very interesting because this process framework, it tells us, for example, that there should be something like a stakeholder needs definition process, but it doesn't tell us exactly how we're doing it. So rather, the process framework invites us to make a customization of the framework on our own, which is guided by a complementing technical report. And it further directs us to the state-of-the-art material, which is typically collected by INCOSE. So you can find everything in the International Council on Systems Engineering Handbook, for example, or you can find some usable knowledge at the sebocwiki.org. So what does this mean? This means that we have a starting point for developing our own process model depending on the needs of our process. And we have a link to typical state-of-the-art knowledge where we can decide, for example, for the stakeholder needs definition process, which methods do we want to apply? And just for an example, if you have some end customers, you will probably apply different stakeholder needs analysis methods than you would do if your customer is, for example, an automotive OEM, like an engineer on the opposite of the table. A typical example how the tailoring of such a process could look like is, for example, ASPICE, which is a development process model that is widely used in automotive engineering and which is used to assess the maturity, for example, of the supply chain. In our case, the most interesting thing in this context is the integration of particular development tasks with particular outcomes that we can find inside our framework. So to illustrate it, we typically separate our development process in 3 phases, like the system analysis phase, the system architecture phase, and an iterative design and development phase with individual process tasks to be completed. And the single tasks here are linked with particular outputs that can be found inside our reference framework, the smart grid architecture model. So this means we have a clarification on what needs to be done. There it is, what needs to be done, and what is the output that is generated. And all together, they hopefully build up the smart grid or fill the smart grid architecture model with our individual smart grid architecture. And by knowing about the different outcomes and the different results from the different tasks, the question may come up how to keep these things consistent. And here we come to one important topic, which is the separation between document versus model-centric development approaches. So for example, a document-centric approach would define particular deliverables and outcomes, and you see different stakeholders or engineers who are in charge of delivering some outcomes, and they are used by other engineers or stakeholders, and they produce something else. And in theory, everything is fine, but in practice, in real projects, in huge projects, it's pretty hard to keep all these different documents consistent. Like, for example, if this is the requirement specification, and here we have an architecture and component design, and maybe you finish this, you finish the architecture, and they start working on the components, and now you're changing some requirements right here. So it's very hard to trace the effect and the consequences. So the opposite approach would be the model-centric approach, which assumes that we have one central model, a digital model, and this digital model is the basis for all information. In reality, of course, this is not one model. This rather would be a set of models that correlate and that interact. But I think the idea comes clear to have one database that stays consistent. We've already discussed this on basis of the creation of a house, where you can imagine that we agreed on 3 different viewpoints. And when we draw these 3 viewpoints with pen and paper, then probably if you change the thickness of this wall on one piece of paper here, then it's pretty difficult to find all the other papers where this very wall will be represented and change the thickness again. So it's okay if you have 3 pieces of paper, but it will be difficult to to maintain consistency when you have 300 or 3000. And for that reason, today we use digital models, which means that all information is stored in one central database, and everything that we see that we are working with is a projection on basis of this database. And if you change any information, in fact, you're changing it in the single database, which consequently means that all the other projections will immediately reflect the change that you just made. Yeah, and with that very simple example, we come to the topic of model-based systems engineering, which is the technical term that we use in that case. And model-based systems engineering is understood as the formalized application of modeling to support system requirements, design, analysis, verification, and validation, beginning in the conceptual design phase and continuing throughout development and later life cycles. So the idea is to have your complete development based on a model or on models through all phases of engineering. And one very important thing here is that by thinking about the lecture from last week, we probably won't find one single model that is suitable for this purpose. Rather, it's about the integration of different types of models that are being used during the development process. So the question is, which type of models do we use and how can we integrate them to maintain one big and holistic picture? And keeping in mind now our generic modeling stack that we already discussed in the last lecture, and now we already see that we have design models, which are the models used by different disciplines like electric engineers, software engineers. We have architecture models, which are basically object-oriented models, which help us with the decomposition of systems. And then on the very top level of this step, we have domain concepts like the smart grid architecture model. And the remaining topic for us now is how can we turn this concept of the smart grid architecture model in a modeling language that we can use inside a modeling tool for creation of smart grid system architectures. And for that purpose, in the next chapter, we want to take a brief look at the development of domain-specific languages. To better understand how the SGAM can be turned into a modeling environment that is applicable in engineering, we need to talk about some fundamental concepts of DSL development, with DSL meaning domain-specific language. As stated on the slide, this is only a very, very limited mini excursus. The topic itself is huge. It's not intended to give you the full understanding, rather it's intended to guide you a direction if you're curious to learn more on that. Okay, so first of all, let's start with some fundamental definitions. So what is a DSL? Well, a DSL can be a programming or a modeling language which comprises syntax and semantics and which is specified or developed to fit a specific purpose, like to fit to a specific domain like an application domain. The opposite of a domain-specific language would be the general purpose language, which is, for example, UML or SysML. Both are languages that could be applied in every domain. The difference is that general purpose languages have a very huge capability as they can be applied everywhere. The drawback here is that by being very capable and very mighty, they are pretty hard to understand, and there is a certain entry barrier for anyone who would like to work with them. In contrast, the DSL has a limited application area, but the benefit is that it is linked to an application domain, so it is typically easier to understand for someone who is familiar with this particular domain. Further separations we can make is between a horizontal and a vertical DSL. Like the horizontal DSL typically is used within a technology stack to cover some technical complexity. So it's a horizontal layer. And in contrast, the vertical DSL is rather used to cover specific aspects of an application domain, like a business domain. For example, like covering aspects from the smart grid. So without referencing particular technology, the domain that is referenced is an application domain. The second differentiation that we could make is between how the DSL is implemented. And in particular, we can differentiate between the internal DSL, which means that it is built on top of an existing language and can also reuse existing concepts, versus the external DSL, which is basically developed ground up. So it is an independent and a standalone DSL, which is much more effort, but gives you also maybe more flexibility. The formalisms that we can use to specify such a DSL in our case is typically done with meta modeling. This comes with a certain benefit in contrast to classical grammar-based specifications or textual specifications, as we know from computer science, because here we have the benefit that we are not constrained by linear expressions, as we can see, for example, in this image. Like if you take the example here, where you take a company that serves a client and a company employs an employee. In this linear expression, we have the problem that the entity company appears twice. And if we want to change it, then we have to change it on two places. The opposite concept here from meta modeling that is based on nonlinear expression comes with something like this, where we can say a company serves a client and a company employs employees. So you already see in this very brief summary that the nonlinear expression that we use in meta modeling has a bit more options than the linear expressions as we know them, for example, from context-free grammars. Well, okay, so now that's how do we proceed with developing a DSL. So it's typically always the same approach. So first of all, we start with gaining some understanding of a particular domain. We try to understand what's the lingua franca, what are common concepts being used, and what could be the basis for the development of our language. In the case of smart grids, our lucky punch is that with the SGAM, we have a very mature concept, which is very well accepted by different stakeholders. And as it is presented by standardization bodies, it finds broad acceptance. So after identifying common concepts, the next step is to specify some language in a formal way, which typically comprises 3 elements. So we have an abstract syntax model, a concrete syntax model, and a semantic model. And we'll talk about these elements on the next slide. And after the specification of our language, we move on. We want to implement it to make it practically applicable, like in a modeling tool. And on this basis now we can further proceed and can validate our language, typically simply by applying it to some case studies, getting an interaction with stakeholders, or whatever you could think about. So before we jump into the steps of language specification and implementation, again, I would like to highlight that this is just a very brief overview, and there are many things are simplified. And the intention of this part is just to guide you the direction where to learn more. It's not intended to be the answer to everything. Okay, but now let's jump into it and let's think about the DSL specification. Well, the specification of a domain-specific language typically consists of several elements. So the three most important things, as mentioned before, are the abstract syntax model, which is something we call it here the hidden underlying unifying structure of a language. Basically, the abstract syntax delivers us the objects and the concepts that we can use to construct some utterances of our language, and it also gives us the relations between objects. We could call it also the grammar. So it tells us which objects do we have and how can we put them into connection. The second thing is the concrete syntax model, and the concrete syntax model is typically the specification of the concrete appearance, like how do elements of the alphabet or of the grammar look like if we want to use them. And the third important element here is the semantic domain model. In the semantic domain model, we typically cover some more detailed expressions of what do individual elements or relations, for example, mean. It's the semantic domain of our meta model. If we go into more, or if we would go into more detail, we also would find aspects like syntax mapping, required language interfaces, and offered language interfaces. But for here, we can skip this. Knowing about the abstract syntax model, the concrete syntax model, and the semantic domain model is enough for what we are planning to do. To get a little bit better understanding, we can try to reflect these concepts on basis of the architecture of UML. So if most of you already know the UML as modeling language, it covers 4 layers. We have the M0, which is reality. Then we have M1, which is basically our UML model. And then on M2, we have the meta model. So basically, we have the specification of which elements can be used for modeling in UML and which relations are valid together with the concrete syntax and the semantic model. And you probably also know that the meta model of UML is further specified on basis of the MOF, the meta object facility, which conforms to itself. So mainly here we talk about the meta model, something that is used to specify a language, which is done here on layer M2. And to illustrate this with an example, we take a closer look to the UML again. And here we see, for example, the abstract syntax model. There the package element is described by means of the MOF again. We see the semantic model, which clarifies what a package means. And we also have some concrete syntax model, which clarifies the visual appearance of the modeling elements that are being used. And to better understand the connection between the meta model and the model itself, we need to take a little bit closer look on the foundations of everything, which can be found in the graph theoretical approach. In that case, we define a model as a combination of a type graph and a set of constraints of various types. So this basically means that a type graph, together with some constraints, can guide how a model will look like, or the other way around. If we have a particular model, we can verify if this particular model is valid in reference to the type graph and the constraints, or if it is invalid. So the simple aspect here is the first one, which is the conformity between the instance graph and the type graph. And as we can see here, for example, with a type graph comprising three entities like an A, B, C with two relations, minor C and minor B. And we have two potential instances that we want to validate if they are conform with the type graph or not. And here we can see on the right side that all these relations and all these nodes that we see here, they conform with the type graph stated over here. And that this instance here on the left side, it also has some relation between the instance of A and the instance of B. And this relation is called minor x. And as we can see in the type graph, this relation is not typed over there. So this model is an invalid instance of our given type graph. So we could also say, if we reflect on UML now, we could say that a model is not conform to the meta model. The second part here between the plain instantiation is the concept of our constraints, which basically further refines how the instantiation can take place. And for example, what we see here is that we have in the type graph, we have given a definition that says we have two entities. One is called C, one is called B, and there is a directed relation between them of minor B. And we need to have in a valid model, we need to have 2 to 5 instances of this connection. This would mean that in instantiation, we would need something like over here, where we have one element C, and we have 3 elements of type B. And according to this, we have 3 relations minor B, which is between 2 and 5. So this one is a valid instance. And on the other hand, in this example, where we have one element C and one element B, so instance of B and instance of C, and we have one relation of minor B, which means that this is outside the specified value of 2 to 5. So this is an invalid instance. So we already see that the existence of a type graph, which mainly reflects our abstract syntax model, together with some constraints, can guide the instantiation of a model that is conform to our meta model in a very brief way. There's just one thing here to mention that is something specific. So for example, if we stick with graph theoretical approach, then it's a little bit difficult to find a more detailed description of just one edge. So for the development of the specification of our meta models, we rather prefer to rely on the meta object facility, which also introduces a concept where edges, like here, are described by means of a node, and this node is of type edge, and it gives us the option to introduce further properties of a particular edge. But this is just a small detail. Again, if you are interested in the development of DSLs, there is a plenty of literature available. This should just show you the fundamental concepts that we are using. Yeah, and coming back to the SGAM, then we can see as an example a limited or an excerpt of the meta model that is used to describe a language based on SGAM. And here we already can see that we have an abstract element for viewpoint, and we have identified a common computational independent model and a platform independent model as particular viewpoints. And we identified different modeling elements like an SGAM business actor that takes place in the computational independent model, or an SGAM logical actor that also takes place in the computational independent model, or an SGAM component which is used in the platform independent model, which basically consists of the lower 3 layers of SGAM. So this is just as an illustration to demonstrate how the meta model as type graph is depicted to describe a language that we use for SGAM based modeling. Following to the abstract model, we also have the concrete syntax model, which basically defines the appearance of individual modeling elements that we choose. And here we have different approaches available. We have chosen for this particular modeling language, we have chosen a library-based approach, which simply means that every modeling element is associated or mapped to a particular image. And then later in the application in a diagram, the modeling element that we use appears like the picture that we have defined in our meta model. This is the most simple approach. It comes with the benefit that it's very simple, but it comes with the drawback that if you want to change a particular style or something, it's a little bit more effort. Okay, and the last thing is the semantic model, which basically is similar to UML, is just plain text describing the meaning of individual elements. No big magic here at this place. Okay, so in a very brief way, we now have seen how the domain-specific language is specified by means of an abstract syntax model, which basically relies on the graph theoretical approach. We have seen the concrete syntax model, which in that case is a library-based concept, and the semantic model, which simply is pure text that is used to enrich the individual modeling elements defined in the abstract syntax model. And after the specification or the formal specification of a modeling language, the next step is to implement this language. And we already learned that we have an internal or an external DSL. And in our case, we decide to make use of an internal DSL for implementation by simply extending UML. So as all of you probably know from earlier courses, UML offers different diagram types, which are collections of modeling elements and relations. And there's one diagram type that a few of you only used, I guess. It's called a profile diagram. And this profile diagram is a pretty interesting concept because UML profiles give us the possibility to extend UML as a language without changing the underlying structure. So this means to a certain degree, you have the possibility to apply your individual styles and individual modeling elements without changing the underlying concepts. Let me illustrate this on basis of a small example. So let's say we want to create our own modeling element, which is called myElement, and we want to give it some property. Then we could say, okay, we take the class element from the UML meta model and we extend it with something that we call a stereotype. And with the stereotype myElement, so if we later use the stereotype myElement and tag one particular class with the stereotype, then this tagged element will become a myElement element, and it will have the property some property. And the same thing is also valid for associations. So you also can extend particular associations. And in the end, you come up with a definition of individual modeling elements and individual relations, and you can pack them together in something that we call a profile, which is a collection of all stereotypes. And on this basis, you very quickly can define your own modeling elements just on top of the UML. This is a very brief concept. Again, it's just to guide you into the direction. So if you want to customize your language or if you want to develop your own language, just take a look for UML profiles. This is a very simple concept that doesn't take too much time. So what do we have in the end? Well, in the end, we have a modeling environment where people will find a UML diagram that looks like this straight behind me. So here you see the SGAM grid pattern as the background of our diagram. So we also managed to tailor the diagrams to appear in this matrix style. Then you find modeling elements like here a use case, which is rectangular, and it shows the ellipse here as a symbol. And then we have different symbols for particular computers, a firewall, or some devices in the field. We already have seen the electric vehicle. Yeah, and also we see the different types of relations that we would like to have in our concept. So what that means now is that people work with object-oriented models, but what they see is one layer of the SGAM cube. So the artifacts that we create, they are still based on UML, they are still object-oriented, but they appear as something that people already know. And this makes it much more comfortable to involve stakeholders in the project into architecture development. So if you want to experiment with it, this SGAM-based domain-specific language, we've published it under the working title SGAM Toolbox. And if you want to, you also can download it at sgam-toolbox.org. It's free to use. So the result here is people see pictures they already know, though they are just projections from a centralized object-oriented model, as we've seen before. And basically, the pictures that people see right here and they are familiar with, they are just projections from an object-oriented model. So we have all the benefits from object-oriented modeling, whilst still being accessible for stakeholders with a non-software background. And the biggest benefit of all here is that if you think now about your SGAM cube, if you imagine to take a look at it from the front, where you see the business layer and the function layer and the three lower technical layers, then you also can maintain, due to the object-oriented nature, you can maintain traceability from business actors on the business layer to logical actors on the logical layer and to components on the component layer. So simply said, this given traceability in object-oriented models means that, for example, if you change a requirement anywhere, you can do some research inside your model to find out what all these what the consequences could be like. This was a very, very brief introduction to domain-specific languages, language development, UML profiles, and the SGAM toolbox. So if you are curious and you want to learn more, again, just check out the SGAM toolbox. And there are also plenty of tutorials on YouTube. So if you want to play around, just go for it. Okay, back to our big picture. What we have so far now, we have a concept for common views that is accepted by stakeholders, is that it's SGAM. We have further detailed it into individual viewpoints and model kinds based on ISO 42010. And now we have an individual DSL, which helps us to turn this theoretic concept into a practical, applicable modeling environment, similar to modeling environments that we know from CAD tools in the civil engineering application domain. And what's missing now is two things. The first one is an answer for the question, do we have best case scenarios or do we have reference scenarios? And also, do you have some proof, does it work? Some examples on solution development and experiences if this concept is applicable to real life scenarios. And that's what we want to take a look at now. So with the SGAM, as we've seen before, and the SGAM toolbox, we have a pretty useful modeling concept and modeling environment that helps us developing smart grid architectures. But what we are still missing is a reference architecture, or in other words, is a concept with elements that we can use to work inside the smart grid architecture. So first of all, what is a reference architecture? We found some definition here. So basically, as most of you can guess, the reference architecture is a blueprint, a proof of solution that helps us defining or deriving individual solutions. So with that said, for the smart grid, we need to search for some concepts that illustrate or that show us which elements typically could be used or which reference solutions exist. And with some research, we found different things that come into handy. So the first one is the so-called ENSO-E harmonized role model, which is basically a construct which tells us about roles that participate in the operation of our grids. So these actors that we identify here further can be used on the business layer to identify which parties are involved. And the second aspect, or the second concept that is very useful in this context, is the so-called NIST logical reference model, which is documented in the NIST IR 7628 guidelines for smart grid cybersecurity. And this is a very interesting concept, because in this concept, they come up with a set of typical actors that are used inside the smart grid. And these actors are already aligned with the different domains and zones that we already know from the SGAM cube. To tell you a little bit more about this logical reference model, the idea of this NIST logical reference model was to identify or to provide a blueprint solution that can be used for the development of secure architectures. And the people that were working on this concept, they made some investigation on lots of studies and lots of work, and they were investigating in detail several use cases they found, and they extracted a huge number of actors, which they finally consolidated into 46 actors. But the most important thing here was that they didn't only extract the involved actors, but they also tried to identify all the interfaces between actors. So they were searching for all the possible connections that they could find. And further, they developed some interface categories. To be precise, they had 22 interface categories. And every interface they identified was assigned to particular categories. And finally, for all interface categories, they came up with the elaboration of different high-level security requirements. So this means, in the end of the story, if you create a smart grid architecture and you know which actor you're going to use, or you are able to find or identify the corresponding actor from the NIST logical reference model, then you already know which interfaces this actor has and to which interface categories these interfaces belong. And finally, you get the security requirements that correspond with these interface categories. So the idea now is, when you develop a model and you use actors from the NIST logical reference model, then you already get the corresponding security requirements. And with the knowledge of these elements, now we can start to combine them and derive one reference solution that can be aligned with the SGAM as modeling framework. So basically, On level of the business layer, we can use the ENSO-E role model, which identifies all the particular business roles that are being used. On the function level, we could use the NIST use cases, which describe the functionality that is typically being realized in the smart grid. And the lower three technical levels, we can use the NIST logical reference model to populate the smart grid architecture here with particular components. And the good thing is that both here, the NIST LRM and the SGAM, they both have the same origin, which is the NIST domain model. So the mapping is a pretty straightforward task. And the result of this, just as a screenshot here, as a result from this here, you can, let's make it bigger for you, like this. You can get, for example, a component layer like this, which shows the individual components. This one I wanted, which shows the individual components. It shows their connections based on interfaces. And as you see here, for example, we have one actor or one component, which is called the metadata management system. And we know that this one has an interface of type U, has an interface U5. And we know the interface category of this. And on this basis, you already can get the individual security requirements. We will browse through the particular model in the next section. And if you're curious and want to explore it on your own, this one is published and you can download it to use it as a template for your own architecture developments. So here is the link at www.en-trust.at/NISTIR. This is where you can find the original model and you can play around with it. Okay, and here in the final part of this second day of the SGAM lecture, I would like to show you some application examples just to get an idea how things would look like in real application. So the first thing that I would like to show you is just the model we earlier discussed, the NIST LRM, which is publicly available at the link that I provided before. So what you find here in this link is an export of the enterprise architect model as HTML, so you can open it in your favorite browser without being in need of installing any modeling tools. So the structure of this NIST LRM here is oriented on the application when you, for example, use it to develop your own architecture. So you can start right here. There you probably could find some description or some textual descriptions of any stakeholders, and then you proceed to requirements modeling. So in the standard structure with functional, non-functional constraints. I'm not going into detail here. And on basis of these requirements, you move over to the architecture development. And what you see here is the image. Just imagine you have the SGAM cube that we have discussed earlier, and you take a look at it from the front. So then up here you have the business layer, here you have the function layer, and below you have the three technical layers, which basically accommodate the NIST LRM. So if we look through all these layers now, we can start off in the SGAM business layer, and here it's just as an illustration. We have the reference to the ENSO-E harmonized role model as a template for using the different actors on the business level. But this one, it's just an image. It's not the topic to discuss here. A little bit more interesting is the function layer, because here in the function layer, you can see on the one hand all the actors, which are imported from the original NIST logical reference model, and they are already mapped to the particular zones and domains. Further, here we have the different NIST categories and high-level use cases. So this is basically a collection. I'm not sure if you can read it. Let me highlight that for you. So this is basically just a collection of the different use cases, or a selection of the different use cases that have, so I need to go over here. There we go. That have been used for the extraction of actors. So for example, you see for advanced metering infrastructure, we have a few use cases for demand response and so on. And these use cases, they're also described in a little bit more detail. And there is also more information available in the original documents. So here we have the use cases and the actors involved. And here you have some guidance on how to apply developing the function layer, which basically always comprises 3 steps. So the first one is you're going to derive particular high-level use cases on the basis of a business analysis. So this means you try to understand which actors are involved, what are their business goals, and what are their business cases. Like, for example, optimize infrastructure usage as business use case for a distribution system operator. And here you could derive particular high-level use cases like data acquisition or control voltage. And on basis of these derived high-level use cases, you could go into the second step, which is the decomposition of a single high-level use case into more granular primary use cases. And that basically results in the SGAM function layer. So for example, for the high-level use case power control, it's again over here. For this high-level use case power control, you can see that it comprises different logical actors executing different primary use cases. So this is basically the identification of more granular primary use cases, which later will be realized. Yeah, and then the last step here, we go to the investigation of every individual primary use case. And here, for example, we have the primary use case control DER, like distributed energy resource. And we elaborate here that the control of the DER consists of different steps. And for these steps, we further derived which information objects are being used, like the P head curve or the Q head curve. And on this basis, we can provide a detailed description, like here we see a sequence diagram, and you also see which particular information objects will be transmitted between different actors that are involved here. And that's just a template. You find more written description on that, but it is just used to illustrate how the function level is developed. And in the lower 3 technical levels here, you can get an understanding of the different scenarios that are being described by the NIST LRM original document. And as you see, we have scenarios for advanced metering, distribution grid management, electric storage, electric transportation, customer premises, and wide area situational awareness. And for these different scenarios, they developed the corresponding combination of actors and interfaces and security requirements, and we brought them together and accommodated them within SGAM. So how does it look like? Well, for example, what you see here is the architecture on the information level for the advanced metering infrastructure. And you can see which components are involved. And not only the components are visible, but you also see my cursor. There it is. You also see the interfaces that are used. And this brings us the following benefit. So for example, if we look inside the, I don't know, let's take the energy market clearinghouse. And you can see that in total, this actor has different interfaces. In the advanced metering scenario, only the interface 17 and 20 are being used. But in other scenarios, the different existing interfaces probably will be used. As we see, it's 133 and so on. And furthermore, what we can see is that for all these interfaces that are instantiated here, they have a type, and the interface type is associated with a particular category. So for example, we see interface U17 can be associated with the category 9, and an interface of category 9, for example, is characterized by the following characteristics. So this is the information from the NIST LRM document, and here you know what interface category 9 means. And the interesting thing now is that for an interface of category 9, here we find the corresponding security requirements. So this means whenever you somewhere have a component that realizes an interface of category 9, then these are the security requirements of a detailed description that need to be fulfilled. And that's the big benefit of NIST LRM and the existence of this one as a template model, because if you create your architecture with the existing elements from NIST LRM, you already have a starting set of your security requirements, which is a pretty good basis, let's say. Yeah, what else do we have? Yeah, here in the communication layer, it's the same thing, but here we see the communication relations, where you can choose on your own which protocol to be used. And in the component layer, for now as a template, we just introduced network modeling, so you can develop your own network segments, your firewall configurations, and whatever you want. Okay, so this is the first example. And this example, again, you can download it, you can use it, you can work with it, and it just gives you a good starting point for developing your own smart grid architecture, because you don't have to start from scratch. Rather, you can rely on existing elements and especially the corresponding security requirements. Okay, then back to the next one. So the second example that I would like to talk about is a real-world scenario from a commercial project. And in this particular case, Boston Consulting Group, or the BCG Platinian, to be more precise, they were developing an advanced metering infrastructure for a major client in Latin America. And this smart metering architecture has been developed as an instantiation of the earlier described NIST LRM. So the complete architecture is developed on that basis. This was a really interesting project, and as it was a commercial project, I'm not allowed to talk too much about it. But if you want to learn more about the project, here is a link to a website. It looks like this. So, and here the Boston Consulting Group, or BCG Platinian, they speak on their own about this project. So everything that is listed on their own homepage, I think I'm allowed to say as well. So if you're curious, you can check it out to learn about the practical application here. From the scientific point of view, what I find interesting in this concept is that on the one hand, the instantiation of NIST LRM and the modeling with SGAM toolbox, it works. That's not the first project. But in this particular project, we had a pretty tight integration between an existing enterprise architecture that was modeled in TOGAF and the SGAM. And similar thing that we see in many projects here is that the IT-OT integration is a big task for many DSOs. And in this particular project, we really had the opportunity to make an alignment and to demonstrate that it's not the question if we take the one concept or the other, but rather it's the question of how to integrate them. And good news, it works pretty well. So the viewpoints being used in TOGAF, so in existing enterprise architectures, are pretty well aligned with the SGAM interoperability layers. So this is a pretty good news for the ongoing IT-OT integration that we are facing everywhere, not only in the smart grid application domain. So if you want to learn more about this topic, not that one project in particular, but the topic in general, then check out our homepage in the publications section. There you will find some publications that consider this aspect in more detail. And the last thing, last application example, which is directly from our research cooperation with Bosch. It investigates the integration of electric vehicles and smart grid architectures. So I can show you a poster that we published at one conference, and you also have a link to our publications. Let me show you the one thing. So as you maybe remember from the first day, we have discussed the topic of emergent behavior in electric vehicle charging scenarios. Like when all cars react to a new price signal, then probably we will see a rebound effect and our power grid could start to become unstable as it starts oscillating. And we wanted to investigate this effect, or we wanted to develop an infrastructure that enables us to investigate this effect. So we developed on the left side the corresponding smart grid architecture models, and on the right side we developed the corresponding automotive models. So the thing is here, again on the left side we see our domain model, and with this domain model we already see that the SGAM toolbox has been used to investigate or to develop the scenario of the smart grid. On the right side, we can see, where is it? We can see that we developed a similar concept for automotive system architectures. This is some work output that we achieved in our research, which is funded by Bosch in that context. And here you already can see that the model, it's called ARAM. This is a model framework that we use for modeling automotive architectures, is pretty similar to the one from SGAM. And the benefit is that these two, or the idea behind this, that these two models are interoperable and compatible. So by further detailing them, like the automotive architecture right here, the object and the design model, which describes in detail the charging behavior of a vehicle, and the object and design model of the power grid, which describes in detail the electric behavior of the grid. And by having compatible models, we are further enabled to integrate them into one huge system of systems model, which is a little bit illustrated over there. So here we have single nodes of single vehicles and photovoltaics and whatsoever. And all these vehicle instances, they behave as modeled here. And in combination and on basis of the Mosaic co-simulation toolchain, we are able to execute a co-simulation which clearly demonstrates the upcoming of an emergent behavior as the power grid here starts oscillating. So that was the research goal, or that is one of our research focus aspects here, to demonstrate how such models can be used to investigate emergent behavior, as we can see in system of systems here. Okay, so again, this is just a brief outlook. If you want to learn more, you're more than welcome to take a look at our publications, and there you will find more of this theory background. And as mentioned again, this is an outcome of our research cooperation with Bosch under the umbrella of our Josef Ressel Center. Yeah, and this brings me to my last slide, the summary and closing. So what did we learn in these two lectures? We made a very rough ride through many different topics, and we learned about challenges in smart grid engineering. We have talked about complexity We have seen about modeling as approach to deal with complexity. And today we learned a few things about which models could be used and how such models, modeling languages could be specified by means of meta models. And we have seen that the result, the SGAM toolbox, is not just a theoretic concept, but it's really it's usable already for architecture development. Yeah, and if you're interested, then don't hesitate. Just get in contact with me, browse through our homepage. You can also take a look at this book where we describe all the concepts in more detail. And yeah, and whenever questions arise, don't hesitate, get in contact with me, and have fun with smart grid architectures. So have a good day and see you next year at this lecture.